Hi there, we are in the module Advanced Hyperparameter Optimization. My name is Katharina Eggensberger, and today we will talk about priors in Bayesian optimization. Specifically, so far this whole module is about how we can increase the efficiency of Bayesian optimization to make it suitable for hyperparameter optimization. And today we will talk about how we can use heuristics that researchers and practitioners have collected and share. How can we encode this as additional priors in Bayesian optimization to improve the efficiency? For that, we will first have a look at where in Bayesian optimization we already have priors. And then we will address the key question, how we can encode such prior knowledge, for example, about the smoothness of our objective function or the expected noise level, or known good regions of the search space, natively in our Bayesian optimization loop as an additional prior. So for that, we need to know where do we already have priors and what do they mean, and maybe how can we adjust them to our task at hand. So priors influence all components in Bayesian optimization. They're at the core of Bayesian optimization. For example, at the initialization, they define the initial design defines the initial evidence on which the surrogate model is built. The surrogate model defines which functions are plausible even before seeing data. And the acquisition function defines the trade-off between exploration and exploitation and how we make the next decision. So more explicitly, in the surrogate model, we do have implicit priors. For example, the kernel family, typically specified beforehand, encodes a structural assumption about our objective function, whereas an RBF kernel has very smooth functions, a matern kernel is more flexible. Secondly, the mean function defines where good values are expected. Typically, the mean function is set to 0, but it could encode trends. Then, optimized during running Bayesian optimization, we additionally shape our model via kernel hyperparameters. For example, the length scale, a small length scale, allows for rapidly varying functions, whereas a large length scale assumes slowly varying functions. So by that, we can already, by modifying and adjusting this, we can already add some of the assumptions or the heuristics or information that we have about our objective or about our optimization problem. But I will talk about also a more explicit way, a method called HPO, Prior Guided Bayesian Optimization. Why that? Because we often do have prior knowledge about what regions in the search space where we do expect the optimum. And we want to inject this knowledge into the acquisition function. The method for that is we do formulate our prior over the configurations. So we define a function on where we expect the optimum to be and then merge this with the acquisition function. And the idea is that we can still run the standard Bayesian optimization loop, but in a slightly modified way with our additional prior. So let's recap. In standard Bayesian optimization, we choose the next configuration. For the iteration n+1, we choose our lambda by maximizing the acquisition function, could be expected improvement. And if we modify that, we introduce an additional prior over our configurations, named pi, hence the name HPO, which biases the acquisition function. And we can simply multiply our acquisition function with this pi, and then we add the decaying factor, so this decays with more function evaluations, so that over time the model has more weight. This guides our search towards promising regions early on and improves the efficiency if the prior is informative. As an illustration, how does this work? So we have here our true optimization function, objective function. This is unknown, but we do have a few observations, the black crosses. If we would build our standard Bayesian optimization acquisition function, we would get this blue line. So our model or Bayesian optimization would think, okay, these regions here are very interesting because we have no knowledge here, so we should explore it. But we can inject this prior here, which is the function pi, as said before, where we say, okay, we do expect our optimum to be in the center of the search space. We don't expect really that very large or very low values achieve a good function, achieve a good objective. And by combining the blue and the red function, we have this modified acquisition function, which would then sample here next. So we have this combination of what we learned from the observation and what is encoded in our surrogate model with a human prior on where we expect the minimum to be. Of course, there are many alternative and extensions to this idea. Instead of user-defined explicit priors, as said before, we can also extract this data-driven, so we can learn this red function here based on data that we have collected on prior observations, prior data sets. But we can also extract these model-driven priors from foundation models. They do encode a lot of the knowledge that we have. And the third alternative is a very different alternative. We can replace the whole surrogate by pre-training a foundation model only on historic hyperparameter optimization data. So we don't use a standard GP and then modify our acquisition function by these explicit priors, but we completely replace our surrogate model with something that we have trained on historical data. The key conclusion and takeaways for this is that additional priors can improve the efficiency of Bayesian optimization by encoding assumptions over promising configurations, especially in the early stages where we have no evidence yet. We can do this implicitly by selecting surrogate models or hyperparameters that match our assumptions about how our objective function would look like, so what is plausible, or about the acquisition function, so how do we want to make decisions and how do we want to select our next configuration. Or more explicitly, we add this additional user-defined or learned prior over configuration, such as in PyBo. Of course, performance depends on how well the prior matches the true structure of the optimization problem. Thank you.